Hello everyone, welcome to this video. In this video series, we will be learning everything about DSA in Python. So whether you're a software developer, a business analyst, a data analyst, or a data scientist, and if you want to learn DSA, this is the one and only playlist for you. So in this video, we'll be talking about the big O complexity, how to measure the performance of a program which we write in Python. So let's get started. Okay, so what is big O? Whenever someone talks about this concept, they're basically asking us, you will always write a program and the program will take some input and then the program will throw some output. Now what this big O notation is asking, what if I give a very big input to the program? How much time does your program take to run? So for a simple example, let's say you are in a library and let's say a lot of books are kept in the shelf. So let's say there are a lot of books which are kept in the shelf itself, and what I tell you to do, I will ask you to only get me the first book from the shelf, always. So no matter how big the shelf is, how many number of books there are, you will always take the same time to get me the book. Whether the bookshelf has 10 books or it has 100 books or let's say 1 million books, I am always asking you to give me the first book, right? So it does not matter whatever the input size is, the amount of time we are taking to execute the task is always constant. And that is what the first constant is, which is order of 1. So we say that our program runs in order 1 of complexity. And you can see here like the code example, I'll zoom a bit. We are just getting the first element from a data list. You can just access the 0th element and always return it. So this is something that will always take order 1 time, and we say that it's constant. Now let's say you are given a bookshelf, like a similar bookshelf, but I tell you that the bookshelf is arranged in an alphabetical order. So all the books that start with A are kept on the top, then comes B, then comes C, and in the end, there is Z. So now I tell you to, let's say, get me a book of Shakespeare. Now one way to do it that you can go through every book, and then when you find, let's say the Shakespeare book is somewhere around here, you can just go and scan every book here, and finally you can always find the Shakespeare book, right? But a very intelligent thing to do here is that you can first check the middle book, and let's say you see that it starts with T. So now you are pretty sure that all of the books which are kept after this, they start with T, U, V, W, X, Y, Z, right? So for sure, my Shakespeare book is behind this book, which is the middle book. So what you have actually decreased the search space of the entire bookshelf to just this upper half now. And now again, you can repeat this thing. Whatever half of the bookshelf is left, you can look at the middle book. Let's say this is the middle book, and you find that it starts with C. So now you know that a book starting with S cannot be kept before this, right? So now your search space has again reduced to half. And this is how you can very quickly find this book. Let's try to estimate how much time does this finding of a book takes. So let's say we have around 100 books. first time you search and divide the space by half, it comes around 50. Then again you divide by 2, it comes, then you have 25 books to search. Then again you have 12 books to search. Then you have 6. And you can see that very fast it will actually come to 1. So 100 by 2 equals to 50, then you divide by 25, 12, 6, 3, and then again 1. So did you see that how quickly you decrease the search space? And this is something which is called as logarithmic time complexity. How many steps do we take? Let's say the number of books is n. We will take log of n to the base 2. I will leave up to you guys to prove this thing. It is a very simple proof and a very intuitive one. And how does this actually look in the code itself? After order 1, we come to order log n. So this is incredibly efficient and it will cut the problem size by a fraction. Usually half. It can also cut it by different numbers as well, right? And like a very good example, one more example is, if we want to find a word in a physical dictionary, we don't read every word, right? We open the middle, decide which half the word is in, and then keep repeating this. So we are eliminating one half of the search space every time. And this is how you can actually implement this in Python. And we will be learning each and every bit of this in the coming videos. So stay tuned for that. Now after this, there is a time complexity called as order linear, which is order of n, where n is your input size. So you can take example, like for example, you are reading a book completely. You have to go to each and every page here, there. So let's say you pick up the Shakespeare book, you have to go and read every page, and you cannot do better than that. So whenever you are going through the input once, then you say that my time complexity of the algorithm is order of n. This is like a very common and a very respectable time complexity. It will go directly with the input size. So if your input doubles, it will take double time. If it triples, it will take triple time. A very good example here is that, let's say you are giving a data list and you need to find the maximum element from that data. So there is no better way of actually looking at each element and then deciding. You have to go to iterate over each data, and then only you can find out what is the max of all, right? So this is order of n, and this occurs very commonly and it is a good time complexity. Now comes the next one, which is order n log n. So you might have guessed it, this is a multiplication of order n and order of log n. This is a very common time complexity that is seen in divide and conquer algorithms. We will be covering everything in details of how this works. You can think of this as, let's say you are given a lot of books. I give you a lot of books and I tell you to sort it alphabetically. How much time will it take? It generally takes us, like all of the best algorithms take around n log n time. Okay, so let's get an intuition of how the divide and conquer algorithm works. So let's say you have 100 books to sort. And first step, what you do is you basically divide. So you divide this entire 100 books into 10 sets of 10 books each. So this set has 10 books, and similarly all of these sets have 10 books. Now what you do, you alphabetically arrange each of these sets differently. I mean, you do it individually. So basically you are dividing first and then you are conquering. Now after you have alphabetically sorted each of these sets individually, what you are left with is ideally 10 books to sort, right? So you don't need to care about the 10 books inside of each set because they are already sorted. So Now your task is just to sort these 10 books properly. So this is the intuition of a divide and conquer algorithm. I urge you to see, like, if you're really interested in this, you can go ahead and see the proof of why sorting a list of numbers takes n log n time. So this is the most common example that you will see. In Python, you can easily do it using the sorted function that we have. Next comes the quadratic time complexity. What is this about? So let's imagine you are standing in a room full of people and every person in this room is shaking hands with every other person. Can you calculate how many different handshakes will happen here? Yeah. So the first guy will shake hands with n minus 1 different other guys. The second guy will be shaking hands with n minus 2 different other guys. So this will go on till the second last guy, and the second last guy will have like 1. So if you add this arithmetic progression, what you will find out, it will be n into n minus 1 divided by 2. So if you see here that if you expand this, it is n square minus n by 2. Let's say we have 100 people. The number of handshakes are happening 100 into 100, which is 10,000 minus 100 by 2, right? So you can see that it is happening in the order of n square. If I have 10 to the power 5 people in a room, it will take 10 to the power 10 handshakes, approximately this much, right? So this is huge. This is huge. And this is a time complexity which is like not possible for very large data sets, and it is not at all optimized. So this is quadratic. Now next we move to exponential time complexity. Runtime will double with each additional element in the output. Now for example, let's say we are playing a game where there is a 5-digit password and we want to guess the password. Got it? And like there is one constraint that the number of characters that you can use is either A or B. So if you see how many different number of passwords are possible for let's say a password of size 5, you can easily calculate that the first place has 2 options, second place has 2 options, third also 2, fourth also 2, fifth also 2 options, right? This will come out to be 32. Now let's say the password size keeps increasing. Tomorrow, let's say you have a password of size 100, it will be 2 to the power 100 number of different examples that we need to go through, right? So this is very huge, and it is almost impossible to get to this number, because if you can get a feel, 2 to the power 10 is around 10 to the power 3, and you have to like keep multiplying 2 to the power 10 for 10 times, right? So this will be around 10 to the power 30, which is 2 to the power 100. Even if you guess one password in 1 second, this will take 10 to the power 30 seconds for you to guess the entire password. This is a very inefficient kind of a solution here, and generally you will see that a lot of recursive solutions follow this pattern. Okay, so now let's try to compare all of these time complexities side by side. So what you are seeing in this graph is all of these different colors represent how much number of operations are being done with the input size. So let's say the input size is 2, the green one represents the constant, blue one represents the logarithmic, the yellow one represents linear, and similarly for all these 3 as well. In the start, you will notice that all of these complexities are very near. So if your input is small, it does not matter whatever algorithm you are choosing, it will take the same amount of time. Just notice that even when the input size is increased to 8, you can see that the exponential one is going too large. The number of operations are 256, right? The quadratic is 64, log linear is 24, and similarly for the other different 3 as well. So as and when you keep increasing the input size, you will see that exponential is crazy. Even with like 30 input size, it is like huge, and it takes a lot of time. So you have to make sure that your algorithm is not getting an exponential time complexity. Let's try to remove exponential and compare with quadratic. So even quadratic, you see it grows not as fast as exponential, but still you can see the growth rate is huge because it basically is squaring the number, right? So if you see here, I am standing around 94 and quadratic is around 8836. All the other different time complexities are very low, which is like acceptable for our case. Okay, so now what we'll do is we'll try to code 2 kind of solutions and we will try to analyze the time complexity for both these solutions. So we have been given an integer array nums and we have to return 2 if any value appears at least twice in the array, and return false if every element is distinct. The first option is to write 2 for loops. So you can write that for I in range length of nums, for j in range length of nums. So the outer loop is also iterating over each element and the inner loop is also iterating over each element. If I is not equal to j, if they're not the same element, right, then if my numbers are equal, so basically it's not the same index that we are looking at, I have found a duplicate here, right? So I can return true, or else I can go ahead and simply return false here. So we'll try to submit this and see how much speed or how much time our solution is taking up. So as we know that the outer loop is taking order of n, right? This one is taking order of n. And the inner loop is also taking order of n. So it's like kind of n square handshakes are happening, right? Every element is going to see every other element, and then we are finding out if there is a duplicate or not. And as you can see here, the time limit has exceeded. So the time limit that was there for this program to run, we have exceeded. Now we'll actually write an optimized solution for this. We will be covering what sets are in the future videos. So let's say we define a set called as scene and we iterate over each num in nums. And what we are doing is that if num is already there in my set, then go ahead and return true because I've already seen it before. And then I will go ahead and add this particular number in my current set. We are just iterating over each number once and we are inserting it in the set once. So this is an order of n solution. And you can see that the solution has passed and the number of seconds it took is 14 milliseconds. Big O and performance of these programs are clear now. Thanks for watching, keep coding and see you in the next video.